Let's take a look at an example on slope of a tangent line. So we are continuing in 3.1. So 3.1 continued. So should have put that up there, right about here. Okay. So let's go ahead and let f of x be x squared plus 1. Find MA, or find the slope of the tangent line at a point. So you're just going to basically do this form or this form. And so let's see, which one did I do? So this case, I used the first thing I defined. I used this. So use this and try it. So put in your function and then simplify this. And I'll erase the blockouts as I go here, and we will look at it. So I like to do this for you. So pause it now and try it and see if you can work it out. Okay, so we'll do this step by step. So you write it out, that's your limit. And so you're going to place in your x squared here, and then x squared, or a squared minus 1 here, and x squared minus 1 here, all over x minus a. Okay, so then substitute in, you should get something like that. Okay, and then you basically are going to distribute this negative across, and you'll see that this, oops, I didn't mean to erase that. That one's, I meant to go like that. These will be gone. Okay, and then I'll erase the next line. Oh, I didn't like that, did it? There we go. Okay, so, and then I'll get all of it now. So there we go. So here's your x minus a. You can factor that. That's just a difference of squares, x plus a, x minus a. Those, of course, reduce. Then you're left with this. And then you substitute in your a, because you can, it's a limit, and you get just 2a. So the slope of the curve, which is basically a parabola, right? It's just a parabola shifted up 1 unit. Right? So that's a parabola shifted 1 unit. Slope of the tangent line is 2a, wherever you're at, whatever value of a is. It's just 2a. So the slope of the tangent line is 2a for any point on the function f. And so you could, I'll do a quick little graph of this, I guess. So you could graph that thing here. I'll do it just real briefly. So here's your graph. And then any point you take, you can see the slope is, you know, it gets steeper and steeper, which of course occurs for 2a. The farther you go out, the steeper the slope, the larger the value a is. And then if you put in a negative value, you can see that you're going this direction on a slope, and it's a negative slope. Okay, let's continue. Now let's do our actual definition of derivative. So this is how we define a derivative, and it is looks like this. So write this down, definition of derivative of a function f at x given by. So we say, this is some notation now, we got to know this. We say f prime of x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0, which of course is the same slope of the tangent line above. Okay, so we say that's the one way to write it. We can also write it in the other form. F prime of a is equal to the limit of f of x minus a all over x minus a as x approaches a. Okay, so that's how we define the concept of derivative. Now, that definition is independent of the actual graph. Like, we don't have to have a graph to talk about a derivative. The function can be whatever. Okay, the function could be about mass. The function could be about velocity or acceleration. The function could be whatever, and then we can still do this same calculation independent of any graph sort of thing. This up here just gives us motivation of why we might want to talk about a derivative, and it has to do with slope of a tangent line. But it really has to do more with rate of change, which we'll get to a little later. So now we're just going to do some mechanical calculations of that. I always have you use the definition a couple times to know what that is, and then we're going to go on to develop like properties of how to take derivatives. So where did I leave off here? All right, so so now let's continue with what I have. I'll write up this stuff as we go, like usual. So if the limit exists at x, or x naught, or a, or whatever, we say f is differentiable at x. At x. Now later we'll talk about differentiability. So just a little side note, differentiability on an open interval. You could talk about differentiability on a closed interval, that kind of stuff. But for now, we're just saying at a point, and then we'll say kind of where those points are. But we need other definitions. We need to talk about right and left. But right now, we're talking about it must be, oh, I wrote that here, didn't I? Must be a two-sided limit. I forgot to mention that. So right now, we're only considering two-sided limits. So we're not considering right now a closed interval. Okay, that's not defined yet, but eventually that's where we're heading. And then it could be defined on all the reals, on R, you know, so you could say it's differentiable everywhere, meaning all the reals. Okay, so that kind of stuff. Here's some other notation. This is other forms of notation for derivative. So if you have y equals f of x, you can talk about, we define basically f prime of x, but here's some other notation. We can say it uses like a d, dy dx is the other notation for derivative. You can say y prime, the superscript is, we call it a prime. We could write it as d dx, and so this basically means the derivative of something, of whatever's here, with respect to x. This is what it tells you the variable is that you're taking the derivative of. So you can say d dx of, say, f of x, right? So all of those mean the same thing. Now, and here's another one that's not used as much, but you can do a capital D with a subscript of y, something like that. So this notation comes from different areas. Basically, once we get into the concept of derivative and rate of change, then you start talking of actual calculus. The concept of limits has been around for thousands of years, like figuring out the volumes of circles area of circles and volumes of spheres was done with infinite, concepts, which is basically a limit. Of course, different, totally not the same notation. It wasn't until the discovery of calculus that we ended up getting this type of notation and the concept of rate of change and integration, which we get to later. So this notation, the prime notation, is attributed to Newton, and the dy dx type notation is attributed to Leibniz. Leibniz and Newton are the ones that independently discovered and published everything about calculus. Oh, and that was in the 17th century, so 1800s, if you put it in perspective, was when this was done. Really not that long ago, if you think about it. All right, so although it is history, this is all history stuff. Let's continue some math stuff, which is really the best. All right, so the derivative of a function is the slope of the tangent line at a point. So that's what we know because that's how I defined it above. Okay, but it can be other things, but that's what I want you to remember, especially right now. You got to have, like, what's the derivative? We'll just say this and you're fine for a while. The derivative of a function is the slope of the tangent line at a point. Okay. So now let's look at basically finding the derivative, but we're not going to, we want to get like what f prime is. So check this out. So let's let f of x, wait, let me back up here. So here's my example. Find the derivative of f of x, and then be careful here. I'm going to say right now, because this is all we have, but eventually I'll say it as well later, by the definition. So later we'll be able to do things by properties, but right now, well, all we have is a definition. But when I ask you on a quiz or something, I want you to do it by the definition, not by the properties. But after that, if I don't tell you, just use the properties. Or this would be really easy if you use a property. That's why we develop properties. Here's the question. Let f of x equal 1 minus x squared. Then we can talk about its derivative. So we can say d dx excuse me, of f of x, or f prime of x, either way. You don't have to write both. I'm just showing you notation. We can say it's the limit of f of x plus h minus f of x all over h as h approaches 0. So I'm really using this definition here. And so if I use this, basically I'll end up getting a function. I'll end up getting f prime over here, or here, whatever. It'll be the prime and it'll have just x in it. Okay, so let's calculate that out. Okay, so you get, this is equal to, and I'll see if I can grab some more room because this does take a little bit to write out. This is equal to the limit, don't forget writing your limit, as you approach 0 of, and then it's 1 minus x plus h squared minus quantity 1 minus x squared all over h. Okay, so that's equal to the limit of, and then you got to calculate that out. You got to expand that out and basically look to factor out h like you did back in, what was it, 2.1, 2.2, and then reduce it. Okay, so you got to multiply it out. So maybe this is a good spot to try it. So stop and try it yourself and calculate this out and see what you get. Okay, so I'll go ahead and so you multiply that out and you get x squared plus 2xh plus h squared minus 1 plus x squared all over h. That's the limits as h approaches 0. And then you distribute and simplify, so it's 1 minus x squared minus 2xh minus h squared minus 1 plus x squared all over h. Okay, so you get this and this to cancel because it's 0. This and this to cancel because it's 0. And then you get that this is equal to the limit as h approaches 0. Then it's negative 2hx minus h squared all over h, which is equal to the limit of h times negative 2x minus h all over h. Got to say as h approaches 0. And now you can reduce that. You can see that's going to be gone. So this guy is gone. And because it reduces to 1. And so we end up with equal to limit as h approaches 0, negative 2x minus h. And then now, finally, you can take the limit. You can take 0, substitute in right here, nothing bad going on, guy's gone, and so you get negative 2x. All right, therefore, we can say f prime of x is equal to negative 2x. So so that's what you can get. I mean, that's by the definition. I always have you look at that. But in the future, we'll develop a property that you can take that derivative and you'll get it done in, I don't know, 3 seconds, 5 seconds maybe, not even that. And you'll know, you can see it, like you can just see, you do something to that with the power of x and stuff, you can see that power is coming in front, right? Power's right there. I mean, you can show this for every polynomial and see what happens. So that's what we'll be able to do. But we got to still develop some concepts here first. So we're going to be doing that. Okay, so let's look at a couple examples. What I'm going to do is have you work these examples out. And I'm just going to go through and talk about them. So I'm going to copy and paste them over because it will take a while to go through these examples. This is the sort of stuff I would normally just do in class, like we do them all together. Or at least I'd have you work on elements of it, and then I'd come back and we'd talk about it. So we're going to basically do a similar thing by me just copying this and then having you look at it. Okay. Move that down so it's on one page, like that. Oops, darn it. That didn't work out so well, did it? Maybe there. That looks good. Okay. So, try all of these. I'll walk through it with you. So, copy this down. Here's f of x. And so we know that's just absolute value function shifted over 4 units. So it's this absolute value function here. Okay, and so what I'm developing here is limits on either side. What's the derivative on either side? So we're going to do one-sided limits and talk about that. So f of 4 is 0, right? The limit of f of x, just f of x, not the function, but just f of x at 4 is always 0. Okay, so if you can always just plug in 4 and you're going to get 0. So it's continuous. So the function this is true. So the limit of f of x equals f of a, because f of a is 0. So since this is true, what can you conclude about the continuity? Is the function continuous everywhere? Okay, and the answer, of course, is yes. Okay, so just this is continuous. So you would say basically, therefore, f is continuous on R. Because that's the only thing in question. To the left or right of that, it's pretty clear you got continuity. It's just, well, what about there? Well, just that little corner is still continuous. Also note, this is kind of for later, but note that if you do the difference of those, then you get 0. Okay, Now, what I want to do next, and this is kind of jumping into stuff I want to talk about without too much development, but sometimes we just got to roll with it. We want to do the limit. Basically, what's the slope of the tangent line on this side? What's the slope of the tangent line on this side? So left or right. So you take 4 and you plug it into the slope of the tangent line formula, right? F of x minus f of a all over x minus a. And now we're going to approach 4 on the left and then on the right. Okay, so if you do this and you approach 4 on the left, then you get absolute value of x minus 4 minus, and that's of course 0. So then you're really just interpreting this. That's just like the quizzes we've done and the few examples we've done. So you know that these values on the inside are basically negative because you're to the left of 4. Therefore, it's a negative 1. And so the whole thing is, or it's negative, the value is negative. Then you divide by this and you get a negative 1. Okay, so look over this again. Make sure this is making sense to you, why you get negative 1. And it should be pretty clear too, like that's your slope right there, that line. Now let's do the same thing and approach 4 on the right. So if you approach 4 on the right, then you're going to get 1, which should make sense because you get this line. That's a slope of 1. Okay, so check that out. Make sure that's making sense to you. So we're getting 2 different limits on either side. So does the limit of f of x as x approaches a does the limit of f of x minus f of a all over x minus a, which is 4 in this case, a is equal to 4, as x approaches 4 defined? Well, they're different limits on either side. The 2 sides are different. Therefore, f prime, we say, does not exist at 4. So that little corner like that is not differentiable. So keep this in mind. This is really important right here. We're going to talk about this as we go. Therefore, we say also f is not differentiable at 4. However, f is continuous on all the reals. Okay, so it's an important distinction we want to make. Continuity does not imply differentiability, but we will show later that differentiability implies continuity. Okay, that's a different statement. I think I get to that exactly next. Yeah, we'll do another video for that. We've still got a ways to go in this section. It's a big section. All right, let's look at another example. Okay, go ahead and work out all this. F of x is cube root of x. Okay, we know this is the graph. Okay, I mean, it's the graph you should know. You could use your graphing calculators. You can use your computers because you're at home or working somewhere with a computer. But you should know that one, what that graph basically looks like. Let's take the limit of this thing as you continue. So if you evaluate this thing, this is what you get. And if you simplify, you get 1 over x raised to the 2/3. So now if you approach 0, this whole thing is going to approach infinity. Now, you're not substituting in 0 directly, right? You can never plug in 0 on the denominator. You can never plug in infinity anywhere. It's what it approaches. It gets close to. So it's approaching or getting larger and larger and larger. So basically this thing is going to infinity. So the slope is basically getting to be infinite, like that. So you have these tangent lines coming in like this, and eventually it's vertical. That's really what that means. Therefore, f is not differentiable at x naught. Okay, so basically it goes in like this, and then right at 0, you end up having a vertical tangent line. Okay, because that's the definition of a vertical tangent line. Okay, it's not the function though. The function is continuous everywhere because we just know it is. We can see it. Okay. Oh, ignore this for now, but that's how you take a derivative and to make it easy on us. We'll do that later. Okay, all of this stuff shouldn't be there. I was just messing with it and I forgot to take the notes out. But yeah, that's how we're going to, so all this work here, oops, I didn't mean to erase that. all that work there can be done in just a couple lines right here, this stuff. All right, so I'm not going to really have that there. We'll talk about that once we derive everything. Okay, so next we will define the theorem. We'll talk about that differentiability implies continuity, but not vice versa.